The first speaker of this morning session, Professor Moshe Marcus from Technion, Haifa, Israel, and he will talk about large solutions for some nonlinear equation with active potential. So please.
Thank you. It is quite exciting for me to take part in this meeting. First of all, because it is for two long-standing friends, and Laurent Veron, and our friendship is maybe already 30 years old, which is quite remarkable. And in addition to that, during this, I actually met Veron first, Laurent Veron, first at a meeting in Paris. I think it was in 92, maybe 91. And at that meeting, we started discussing some problem. And I think that our first paper appeared in, our first joint paper appeared in 93. And the last one in 2016. So quite a period. I'm sorry that I didn't have collaboration with Marie. I always admired her work, but somehow the subjects in which each of us concentrated were near, but not near enough. Okay. The choice of subject, by the way, was influenced by the fact that at least during the first 10 years of our collaboration with Laurent, there were quite a few works on large solutions. So this is another one in the same spirit, but in with some very new features. So yes, and of course I wish to thank the organizers that I think did a wonderful job, and I greatly enjoyed the first day of talks that I heard. Now, let me describe the problem. It's very easy to describe. You are all familiar with the equation minus Laplacian u plus fu equals 0, where f could be an absorption term as it is here, or a source term. But instead of the Laplacian, we now look at this operator where delta is the distance to the boundary, so mu over delta square is the Hardy potential, let's say. And the whole talk will be concentrated on one topic only, uniqueness of large solution for arbitrary positive mu. There are I have quite a few things to say about negative mu, but that's an even longer story, and so I will not try to be too ambitious and just discuss mu positive. Now, the basic features of the nonlinear term f, that it's positive, monotone increasing, superlinear, but we shall describe more precise assumptions later. Now I want to mention some previous works, mainly works on large solutions of equation 1, the equation that we saw before. This is equation 1. Because, of course, for this problem, there are so many papers that I'm not trying to make any overview or catalog. So I'm just mentioning a few previous work on large solutions of EQ1. Well, one of the first that I encountered was by Bandle, Moroz, and Reichel from 2008. They studied the problem, this problem, where Fu is a power, u to the power p, p greater than 1. They established several things. First of all, an extension of the Keller-Osserman inequality. Otherwise, there is not much hope of the existence of a large solution. And then they proved existence, not uniqueness, but the existence of large solutions in several cases, which I'm listing here. Incidentally, for mu less than 0, there is this limit 1 minus 2 over alpha minus, which I should not discuss, but this is a very important limit, because for any p greater than that, the equation has moderate solution. For p less than or equally doesn't have moderate solutions. Okay. A long jump to a paper of Du and Wei, I'm not sure how it's pronounced, from 2015. They studied the same problem, but they proved much stronger result, existence and uniqueness solutions for arbitrary mu greater than 0. But I emphasize it's just for the case of powers. Okay, next. Well, there was some work of Bandle and Pozio very recently where they even discussed sublinear problems with powers, but sublinear. Another paper of Bandle, Moroz, and Reichel from 2010 studied the equation in the case of the exponential. And that's remarkable. It's the only paper that I know from the past that discussed the question of large solutions and existence uniqueness in the case of the exponential. It's indeed very different, although their work was based on the standard idea of creating sub and super solutions, but very delicate constructions. So they proved that if mu is positive and less than the Hardy constant, there exists a unique large solution. It's interesting to note that in this case, large solutions may become negative when away from delta omega if the domain is large enough. So it's not exactly positive solutions here. So, in addition, there were many works on this potential, mu over absolute value of x squared, where 0 is a point on the boundary. Here I list some of them. There are many. I'll just mention that recently there was quite a bit of interest in the question of boundary value problems for equation 1. The works concentrated on the case of power nonlinearities. The problem is how to define a boundary trace here, because for instance, if one looks at the measure boundary trace, then for mu positive and less than the Hardy constant, it's always 0. And for mu negative, when it exists, it's always infinity. So how do you distinguish between different boundary traces? This was a very interesting problem. It is a very interesting problem. And there were a number of works which I am mentioning here. If the methods in the 2 papers by Nguyen and myself and by Gikas and Veron are quite different in the definition of boundary trace, but in a later paper of Gikas and Nguyen, it was shown that they are equivalent. Of course, these papers also contained some results about large solutions, but this was completely a side question. The main question was the boundary trace. Now, what are the conditions on nonlinearity that we are going to assume? I don't insist on the best condition as far as the regularity of the function f is. Let's say that it's in C1, but not in 0, 1, as I wrote here by mistake, but on 0, infinity. Here it should be infinity. F0 is 0, f prime is positive, and f is convex on 0, infinity. So this is the first set of conditions, F1. The second condition is this. Let's denote by H the function given by Ft over T for positive T, of course. So the assumption is there exists a constant A ds such that HUX is bounded by A times delta to the power minus 2. This is a basic assumption in potential theory, which we shall employ in some parts of our development. This is assumed to hold for every positive solution of the, let's say, classical equation, minus Laplace nu plus fu equals 0. Okay, these conditions, of course, hold for a large family of functions. I'll mention a few more details later. One of the things that I'm particularly interested in is that the assumptions should include the exponential, which they include in this case. Not only this exponential, but many exponential functions that we can construct. Now, condition F2, that's to say this condition, it says that U is bounded, it implies that that all solutions U are bounded in compact subsets of the domain. This implies the Keller-Osserman condition, which is the one that you see here. Under some results about existence and uniqueness of large solutions. So condition F1 implies that in a bounded Lipschitz domain, the equation n is 0. This is the equation minus Laplace nu plus Fu without the singular potential possesses a unique large solution. We shall denote this solution by U F omega. Conditions F1 and F2 together imply that if omega is smooth, then U F omega, the unique large solution, behaves like phi. Phi is the inverse of psi. This is psi, so the inverse of psi is phi. And so we have precise behavior in the case that omega is smooth and under conditions F1 and F2. There were some weaker conditions later on, I think. Condition F2, which, as I mentioned, condition F2 relates to positive functions of the classical equation minus Laplace nu plus Fu equals 0. It implies a similar inequality for solutions of EQ1. The difference is that here we look at HU over A1, where A1 and A0 depend on F and omega. This is from a paper with Nguyen, very recent. Just another remark, condition F1 implies that this function H is monotone increasing because of the convexity, and that F0 is 0 and so on. Monotonicity and convexity will imply this. Now I'm going to describe the main results that I'm going to discuss. The first theorem works in a bounded Lipschitz domain. And for this, we need only that F satisfies F1 and F2. Actually, we don't need that much even, but let's assume that. Then for every mu greater or equal to 0, there exists a large solution of equation 1. And in particular, there exists a large solution which is bounded below by the equation, by the large solution of the equation without RD potential. This is, I called it a theorem, but it's almost trivial, as you will see in a moment. Theorem B, wow, I didn't realize that this. Theorem B is in a C2 domain, again assuming F1 and F2. If mu is non-negative but less than a quarter, then EQ1, the solution with Hardy potential, has a unique large solution. This theorem is interesting because it applies to the largest family of functions that I worked with in this respect, in this context. As you'll see, it's also interesting because it has some relation to an old paper of mine with Laurent, which appeared, I think, first in '93 as an announcement, and the paper itself in '97. This is probably the main result of this talk. Again, omega is a bounded domain. I assume F1 and F2, and a few additional assumptions on H. I suppose that it's not so easy to verify them in your head right away, but they do hold trivially for powers, and they also hold for exponentials, and that's, as I said, my main interest, that the result should apply to exponentials as well. This also holds for this class of functions that I mentioned. Okay, under these assumptions, for every mu positive, the equation with Hardy potential has a unique large solution in omega. So the existence is rather trivial. The uniqueness is a rather deep, much deeper result. Now, I see, I'm looking at my watch. Some comparison with previous results. I mentioned the result of Du and Wei that proved the uniqueness of large solution for every positive mu, but this was only in the case of powers, and their proof was strongly dependent on special features of powers, e.g. similarity invariance. But naturally, necessarily, Theorem C is based on an entirely different approach. The result of Bandle, Moroz, and Reichel concerning the exponential could be compared to our Theorem B. Of course, our Theorem B is for a large class of functions, but it contains the exponential in this form, e to the exponential to the power u minus 1. This, of course, means that all large solutions are positive everywhere, contrary to the situation with this, with Fu equal EU. We allow mu to be less than a quarter. In the paper of Bandle, Moroz, and Reichel, they assumed mu less than the Hardy constant. The Hardy constant is always smaller than a quarter, so this relaxes the assumptions. Still, the two are very close, and nevertheless, this was surprising for me, the large solutions near the boundary behave in a different way in the two cases. It's best to, let's say, this is the large solution in the case where Fu is just e to the power u. It's best to look, well, V behaves like this, but it's interesting to look at H of Vx. Remember, H is Ft over T. H of Vx behaves like this, not like delta x to the power minus 2. Actually, it increases more slowly. On the other hand, in the case EU minus 1, mu up to 1/4, the large solution fluctuates between this bound, H of the large solution, fluctuates between these two bounds. This is the same as there, and this is the upper one. And the point is that the upper bound is achieved for arbitrarily small delta. So definitely the behavior is different. About the proof of Theorem A, we'll make it very short. Since mu is positive, UF omega is a subsolution. This should be EQ1, I'm sorry. I changed notation at some time. This is our equation. Um, so being a subsolution, and we can construct the smallest solution that dominates it by means of an exhaustion of omega, standard procedure. Since we remember that we have the Keller-Osserman condition holds, then of course the sequence that we construct in the exhaustion omega is increasing and locally bounded in every compact set. Therefore, the limit exists and it's larger than UF omega. Well, it's a large solution of our equation. I'm sorry about the mixed, my confusion with two different notations. One of historical value and one that I'm using here. This should be EQ1. So, as I said, this is essentially a very simple fact. Now, on proof of theorem B. Theorem B, let me remind you, well, I shall simply go back to show you. Omega here is a bound, well, actually I say bounded C2 domain, but it could be a Lipschitz domain as well. We assume that F satisfies F1 and F2, mu between 0 and 1/4, then EQ1 has a unique large solution. So I want to give some ideas about how this works. We start with, okay, assume that you have two large solutions. We may assume, without loss of generality, we may assume that there is U1 is less than or equal to U2. Otherwise, we replace U2, we take the maximum of the two solutions, which are, the maximum is of course a sub-solution, and take the smallest solution above it, and that's it. So we can assume that U2 is larger than U1. What we are going to show is that the lim sup of these two, U2 over U1, as X goes to the boundary, is actually smaller or equal to 1. And of course, this implies that U1 is equal to U2. This is the setup. Now, in order to prove this fact, that lim sup of U2 over U1 is less than 1, we need a construction that reminds me of one that we used in a paper with Veron, with Laurent Veron from 97. There it was for the proof of uniqueness for the equation without Hardy potential. So the construction, I mean, the end of the construction is the same, but the construction itself is very different in the present case. Rather, I would say the way it is achieved is very different in the present case. Well, here I should have had some figures, but unfortunately, I didn't know how to introduce figures in the PDF file. So we'll have to use our imagination. So we look at a point on the boundary, and we denote by TP a cylinder. So first of all, let Xi equal Cp be an orthogonal set of coordinates centered at P. Xi equals 0 is P. And the axis is the Xi1 axis in the direction of the quasi-normal into the domain. Why do I say quasi-normal? Because I really thought about Lipschitz domains, but if it's a C2 domain, it's just the normal into the domain. Okay, so this is the cylinder that I am considering. The height is rho, and the width is r. Well, since omega is Lipschitz, for every p in delta omega, there exists a set of coordinates as above, and numbers rho and k, such that there exists a function, a Lipschitz function, on Rn minus 1 with Lipschitz constant k, which vanishes at 0, which means at p, and such that this function actually describes the part of the domain of the boundary of omega that lies within the cylinder. If I look at the part of the cylinder that is within omega, it's bounded between this manifold Fp Xi prime. Xi prime is in Rn minus 1. And I denote by Qp this cylinder. R is chosen very small. It doesn't matter for our results. So as to guarantee that the manifold described by Fp stays away from the top of the cylinder, from rho. Okay. Once we have this notation, basic notation, we now are going to, we'll construct a subsolution. I'm not going to construct it, I only describe what we are doing, what we do. We construct a subsolution W of EQ1 in this domain, which is the same cylinder. I mean, it is within the intersection of the cylinder with omega, but it has half the height and half the width. And I call it Q prime. And we are going to construct here a subsolution of L mu, which is continuous in the closure of this domain intersect omega. That's to say, it's continuous in the part of the domain that is contained in omega. It's of course not continuous on the manifold Fp. There it will be infinity. Anyway, it's continuous in the part of the domain that is contained in omega and vanishes there. On the other hand, on the part of the cylinder which is on delta omega, there this subsolution behaves like U2. So it's a substitute for U2 in a way, because we cannot construct, in the present case, we cannot construct a solution like this. We can construct a subsolution, but that's enough. So what are so this W explodes on the boundary of Q prime that is on delta omega. and it is 0 on the part of the boundary that is within omega. The existence of such a thing is based on two facts. The fact that L mu has a green function in a strip, one-sided strip around the boundary. Omega rho is a strip, say, delta between 0 and rho. And the boundary Harnack principle applies to L mu in this strip. And these two facts that we need follow from the assumptions that omega is Lipschitz and that mu is less than a quarter. And I want to point out that we do not require mu less than the Hardy constant, because the entire construction is within a thin boundary strip like this, delta less than rho. And it is known that in such a strip, the Hardy constant is always 1/4. This was proved in a paper with Meisel and Pinchover from '98. It was so this is what we construct, this is what we should keep in mind, that W is continuous in the domain up to the boundary that is contained in omega, vanishes on that boundary, but on the part of the boundary that coincides with the boundary of omega, W tends to infinity exactly like U2. Okay, so suppose that we have constructed this. The construction is indeed delicate and there is no time to discuss it. Once we have this construction, we look at the shift of the function, which of course is defined in a slightly smaller cylinder. It's not up to half rho, but up to half rho minus beta. Beta is just a small number, as you see. And then we can show that the shifted function is also a subsolution. Here we use the fact that mu is greater than 0. It does not work if mu is less than 0. And in addition, so it's a subsolution in this smaller domain. And it is less than U1. Why is it less than U1? Because it's 0 within on the boundary of Q prime beta that is within omega, and U1 is of course positive there. And it is finite on the boundary of the domain, because you see, we take, instead of the values of W itself, we take the values at Xc1 plus beta, so finite. And there U1 is infinite, so W beta is less than U1 on the boundary of this entire domain. We can deduce that W beta is less than 1 in Q prime beta. And since this is true for every beta, we get that W is less than U1 in Q prime. And now let's recall that W behaves like U2 as Xc tends to the part of the boundary that is on delta omega. So from here, I can deduce that the lim sup of U2 over U1 is less than 1 when Xc1 tends to Fp Xc prime. This is the manifold that defines the boundary, and Xc prime, let's say, is R over 4. since we can prove this for every P, we have such a neighborhood with exactly the same R, then of course it follows that this is true when Xi tends to the boundary of delta omega. And from this we deduce that U2 must be equal to U1. Now, well, I have little time left for the last theorem. I will describe the main steps without going into proofs, of course. Let me remind you again of the theorem. Theorem C was about the existence of a unique large solution for the equation with Hardy potential for arbitrary mu positive, and we assume F1, F2, and some additional assumptions on H, which all hold, of course, for powers, but also for exponentials and for relatively large class of nonlinearities. My interest in exponential was because it's, in a way, the simplest example where you don't have the similarity invariance. Once you have the similarity invariance, it's possible to prove this result in much for more functions, not just for powers, but for there is a whole sort of functions, a whole class of functions where the similarity invariance works. But those functions will be dependent. It will be a function f will depend on x and u, not just on the function itself. And for all those, it's possible to prove this result. Not in the way that I'm doing it here, but in a more classical way. Okay, so the first step in the proof of theorem C, there exists a maximal solution, of course, because the set of all solutions is bounded in every compact subset of omega. It's greater than UF omega. Well, this we already mentioned in theorem, in the first theorem A, that UF omega is a subsolution and there exists a large solution above it. So the maximal solution is certainly above it. And it's also bounded by A phi delta, where phi delta is just h minus 1 of delta minus 2. For instance, in the case of powers, this is delta to the power minus 2 over p minus 1. But remember that in the case of the exponential, this will not be this will not be what you expect. That's to say, h of phi, not of tilde phi, is different from this. It's delta minus 2 divided by log delta, log 1 over delta. Okay. Now, this is that if U is a large solution, then the limit lim sup of HU times delta square must be greater than mu. I will not explain this here, and it's actually true not only for large solutions, but for a much larger class of solutions. But this I will not have time to discuss. However, I want to point out that here you have that H of the maximal solution is less than H of a phi, which behaves essentially like delta minus 2. H of a phi will be essentially like delta minus 2. So, or less, it will not be like that, it will be less than delta minus 2. While here you get the inverse inequality, that HU is greater than mu over delta minus 2, than mu times delta minus 2, but you don't have it for U, it's just the lim sup that satisfies this. So it's not so easy to use this because it's just the lim sup, but if omega is a ball or the exterior of a ball, and we consider radially symmetric large solutions, and exist radially symmetric large solutions. In fact, U max is a radially symmetric large solution. And it is the unique large solution in the class of radially symmetric functions. Now, the point is that if it's radially symmetric, then the lim sup means that there exists a sequence delta n that goes to 0 such that HU max is greater than mu over delta n square. That's a very important fact, which we cannot directly obtain in a general domain, and you'll see how, nevertheless, we'll get to it later on in general domains. Well, so at this moment, we know that in this radially symmetric domains, BR0 or B prime R0, there is a unique radially symmetric solution, unique in the class of, a unique large solution in the class of radially symmetric solutions, and that it behaves in the way described here in 2. Now, of course, we want to get from here to general domains. So how do we do that? Given a point P on delta omega, we can find a ball such that it just touches the closure of omega. That's to say that the closure of BPR intersect the closure of omega is only the point P. And I denote by UPR the radially symmetric large solution in the exterior of BPR, or of the closure of BPR. Well, omega is contained in Rn minus BPR, and therefore, and here again we use the fact that mu is greater than 0, this UPR is a subsolution of equation 1 in omega. So if I compare it with a large solution in omega, UPR is finite except possibly at P, and to get, well, I have that UPR is less than or equal to U. Perhaps you have to move it a little bit to the outside to get this inequality, and then it also holds in the limit when you push it back so that it touches the domain at P. So UPR is dominated by any large solution of EQ1 in omega. Since omega is smooth, we may choose a radius r like this, with all these properties, which is independent of p, which is good for all p. And now just imagine that you are rolling this ball which touches the domain at p, you are letting it roll all over the boundary of the domain. And now you look at the maximum of all these functions UPR. So we said that each UPR is a subsolution, the maximum is again a subsolution. And since each of them is less than U, the maximum is less than U, where U is an arbitrary large solution of EQ1. Now the smallest solution dominating W is a large solution because it blows up at every point P. UPR blows up only at P, but the maximum blows up at every point P. So it's a large solution. Well, since this, so I'm looking at the smallest solution dominating W. It's certainly less than or equal to U for any large solution U of EQ1 in omega. Therefore, it is the smallest large solution of EQ1. And I denote it by U omega minimum. Well, one can see, perhaps it's not easy to immediately imagine it, but from this, we can deduce that HW is the maximum of UPR. HW is greater than mu delta n squared for a certain sequence delta n that goes to 0, which depends only on the R, the radius of the balls that we considered. And of course, it's greater than, U minimum is greater than HW, so we have this inequality on gamma n, only when delta x equal to delta n. The same sequence delta n that we had before here, and which depends on R, but R is fixed. Okay, from here, we can prove that the maximal solution, there exists a constant m greater than 1, such that the maximum solution, maximal large solution, is bounded by the m times the minimal solution, not in all the domain, in the whole domain, but on gamma n. Well, but if it holds on gamma n for every delta n and delta n goes to 0, we deduce that indeed the inequality holds in omega. And then by an argument, a convexity argument from a joint paper with Laurent from '98, we know that this implies that U max is equal to U min. That's to say the solution is unique. Well, perhaps I am a few minutes late, but thank you.